All right, let's see if our PowerPoint will crash this time. Hopefully not. And now it's actually going to work. All right, so what I want to talk about is communications pathways, cables. On-campus students get tortured a little bit because I make them look at and use some of these. They have to make their own Cat 5/6 cables. So what we wanted to cover in here is some items just really quickly and looking at it that way. So one of the things that I want to make sure everybody realizes is this idea of bandwidth versus throughput. And bandwidth is really a term that's gotten taken out of context, but now it's become our standard, kind of like a search engine is, hey, I'm going to go Google that, when reality is you could be using a number of different search engines. Bandwidth means, at least in the context of what we're looking at, is what could we theoretically send or receive? And throughput then is that measure of how much we actually send and receive. So to make life easier for us, both are used, those bits. So remember those zeros and ones in binary come into play here. Because, well, for a whole variety of reasons. But when I go out and I get a service, so if I go out and get Windstream, it's going to say, hey, you can get 100,000 bits per second. Well, part of that is marketing because it sounds better. Because if I said bytes, which are actually our smallest useful piece of data, then it would make it seem like we were 8 times slower than if we said, hey, we've got bits, right? So there is some marketing speak in there. These are some terms you should be aware of, just to kind of have these nomenclatures. And if you've had some science courses, you've seen this, where you have kilo means 1,000, mega means 1,000,000, giga means 1,000,000,000, and terabyte, trillions. And so now we're getting speeds into the hundreds of megabits per second. Sometimes we're getting them, depending on where we're at, we can get faster than 1 gig service. If you had the resources of Bill Gates, you could probably get a terabyte per second connection, but nobody on the other side would be able to push enough data to you. So make sure you've looked at that and you remember those ideas, because we're going to come back to that, and we're going to look at what our own speed is on our connection here. So I'm going to go kind of weird popping forth here. So one of the things that we look at, and one of the issues, is something called crosstalk. And so if I envision the wires laying side by side, and so the way I always do it is I lay out my arms in front of me, and I hold them together. And they're kind of roughly parallel, right? And the longer I have things parallel to each other, the more that voltage and that signal can go from one wire to another wire, because I'm exposing them for a long distance, and it becomes easier to do. Well, the way we fix that or modify that in most of our cabling now is we put those twists in it. And so if I take my hands that are out in front of me, and I know you guys in class are like, oh, he's crazy. And I grab my hands and I do like a twist like that. Notice how where my hands meet, that I'm at almost a 90-degree angle. So the tighter the twist, that minimizes that length where they're parallel. And so that's one way we get rid of that idea of something called crosstalk. It's one of the flaws we can have. So, kind of going backwards to show you where we're at. So noise is anything that's on there that we didn't want. And we can have noise from all different kinds of things. We can have motors, we can have copiers, fluorescent lights, you can have microwaves. So that's that idea of electromagnetic interference. All different kinds of things. Maybe you drive by Offutt Air Force Base and all of a sudden your radio doesn't work. Well, they're probably putting out some signals that are causing you some noise on that. Crosstalk is when one wire crosses over to another one. All right. There's a couple of terms that are a little weird. So alien crosstalk means 2 cables. Okay. Far and near end depend on where you are located. If I'm at the Auburn end of the cable, then the near end is in Auburn and the far end may be in Nebraska City. But if I flip that around, so you have to make sure you specify where you're measuring it from, whether it's at the end or at the other end. So In class, I have an entire sheet up there from Fluke Networks underneath the TV on one wall that has some of the different types of signal issues that we can get. So near end, if it's biased, it's typically the connection point has been wired incorrectly or they've done something weird, and far end's the same way. It's just those endpoints tend to have some kind of an issue. It just depends on how we want to look at it. So there's a couple of other things that we want to look at, and one of those is something called attenuation, or the signal gets smaller and smaller and smaller. So when I start driving outside of Omaha, and I'm listening to, what's a radio station in Omaha? Does anybody listen to one? All right, 98.5, whatever that is. And the further away I get from Omaha, that signal goes down in quality, right? Well, that's the same thing that happens to our signal. The further we push it, it starts losing strength over and so strength in this case on this divide on this chart here, we're showing strength as this how high above zero it is, how many volts there are. So the problem then we run into is how do I then resend that signal, or how do I fix that signal? So the first model, so notice we've got this noise, and because these are zeros and ones, they're like little square pulses. Does that make sense? So this is a 1, that's a 0. This is a 1, that's a 0, where we're down. So when I get that noise on there, my square wave starts looking pretty ugly. If I use a repeater, or another term you might hear is something called a regeneration, so it takes that digital signal, reads it, and then resends it, and so it's perfect again. Well, that's good. The problem, or one issue, is if I have multiples of those repeaters, that adds time to my communication from one end to the other. So when we talk about fiber optics, where I was in, we would actually generally have to put a repeater in about every 70 miles. So between Omaha and Kansas City on a fiber optic we did, there's actually 2 of these repeaters. And each time we have that repeater, it adds a little bit of time delay because it has to read it and then resend it. So repeaters are great, but we do have to realize that it does have a little bit of a time issue. And the time issue, we call that as latency. So when I say we have latency, it's that delay between when we send something and when it gets there. So if it's long enough, that latency, then it may cause errors for us. One of the things we have to remember is how fast is that signal being sent on that wire? Is it the speed of light? Is it slower? Can we figure out what that speed is? That's where everybody's head nods and they go, yeah. So other things that can happen. The length of the cable can cause that length, because obviously the longer the cable, the longer it's going to take to send and receive. If we have any devices like those repeaters in the way. And then we have this term round trip time. How long it takes to go to a sender and then back. So if they have different amounts of delay, then they receive it out of order. And so I'm going to open up my command line window here and drag it over. So that RTT time, let's take a look at it really quickly. And so I'm going to do a ping, and I'm going to simply ping google.com. So this reply tells me how long that trip took to get to and from there, 17 milliseconds. So obviously that's some distance away. If I do it to, let me do it to our own server in here. Well, you guys can. It's going to show something weird here, but let me just do ping. Because remember, I'm on the faculty network and you guys aren't. So here it's going to give me, it's going to fail out. Let's try something I know is fairly local. Ping. ping unl.edu. I can't type and see what I'm saying there. Okay, ping, P-I-N-G, unl.edu. And so that one should come back pretty quickly. So notice, to and from, we're at 5 milliseconds. That's pretty quick, right? If I could ping our server back there, you're about 1 or 2 milliseconds. So that distance has some effect. So I'm going to try one I know that happens to be in Australia. Now, I'm just going to put the numbers in. So it's 139, 130, oops, that's the 0, 4.5. So I'm going to hit my ping. Oh, I thought I would. Ping. There we go. So now, notice how long that took to send and receive. 185 milliseconds. So that's significantly longer. The other thing I want to notice is we talked about that time to live telling us how many devices are in between there. So when I sent off a ping to UNL, obviously that was a 128 that it powers a 2. And so it took essentially 7 hops, and we'll show you that what it looks like. In this case though, because the way I put it in there, it just set that TTL to 255. Oh, there's a lot more hops there. So I'm going to do a trace route to that same address, 139.130.4.5. Now let's see if it'll show us anything interesting. And you could certainly play along. So there's our campus. There's UNL. Now we're getting off onto different pieces. Here we're on the Ethernet 2. So you can kind of see where we're going. And if I look at the times, I'll scroll up here in just a second. So if I look at the times here, so here we're all the way out to Wiltel's, and we're at 43 milliseconds. So we're getting further and further away. You can see that. Only 1 millisecond to our own router, 3 then to part of UNL. Now we're getting some more interference here. And then we're up to 45 milliseconds. But notice we take a giant jump here. So we go from 45 milliseconds roughly to the 180s. What do you think happened there? Would it help if I told you that this location was in Australia? So here we've hit the border of the United States and we went on submarine cables, and that distance is pretty huge. So now you can see that we've got to Sydney to Lestra. We have a lot further distance we've had to go, and that time difference to get there makes sense. All right, so that's that idea, that latency. All right. Here's the weird deal. If you guys have ever used a CB, that is that idea of half duplex. We can only send signals one direction at a time. Most of our plugged-in connections are now duplex. Here's where we see half duplex is when we are sending wireless, because we can't send wireless signals both directions. So think of those walkie-talkies, and we have some ways around it, and we'll show you what we're going to do. All right, couple of other terms that are a little weird and odd in here is the idea of multiplexing. So multiplexing allows us to put more than one item on those set of cables, or on that coaxial cable, or on that fiber. At one point in the not that far ago, in fact in my lifetime, there were only about 28 coaxial cables from the East Coast to the West Coast, but we were able to carry all the traffic on it. And even now, some of these very large capacity fibers we think of, so for example, it's now CenturyLink, but it was Level 3 Communications from Omaha to Denver is only 144 fibers. So they're not as huge, so we have to have a way to put these together. And so we do that by multiplexing, so we can put multiple signals on one type of cable or wireless or wired, whatever we're doing. So we're breaking them into subchannels. That makes sense. So we have a multiplexer that combines them, and then we have a demultiplexer that takes them all apart. So, a couple of ways we do it on copper lines. And we've been doing this for a long time with copper, because running a copper line out to everybody's house is a little bit problematic. And the way we first did it, and then one of the things we did was people used to be on these shared party lines. And if you grew up in the country, you may have seen those before, where 8 people were really all on the same phone line. Well, that doesn't work, so we have to come up with a way to break them up. So our most common ways we do that are on copper, are TDM, or time division multiplexing. In other words, each subchannel gets a certain amount of time. Maybe they get 10 milliseconds, then channel B gets 10 milliseconds, and channel C gets 10 milliseconds. That works, but if I think about it, what if channels A, B, and C aren't transmitting anything and only D is? Are we wasting those time cycles? Yeah. And that's where this idea of statistical time division multiplexing comes about. And so it adjusts that who gets what time slots based on what you're trying to send. So it maximizes or makes it more efficient. The other way we can do that is frequencies. So if you have DSL at your house, you're doing that right now, because you had to put those little filters in, because the frequencies of that DSL signal are higher than what we can normally hear. And so we break that into different bandwidths so we can send it that way. Well, we do the same type of thing on fiber optic cables. So we call it wave division multiplexing. We send different light beams or different colors into that fiber. Dense wave division is kind of the more expensive, if you want to think about it that way. It's very tiny little channels, so we can send, in some cases, 250 or more different streams into one fiber optic cable. So this is one of the reasons we've been able to reuse some of the fiber that's been out here 20 years in the ground. We just keep adding more subchannels to it, and we send them. Coarse wave division means that the channels are much bigger, so maybe we can only get 16 channels or something, but it's a way we could put multiple channels from here to the administration building, for example. And it's much cheaper. So both of these rely on a little bit of something that you guys have all seen before. So it uses something called a fiber Bragg grating. Oh. Well, you've seen something similar. When you see a rainbow, or if you guys have got to use a prism where it splits out all the different light signals into different wavelengths, that's essentially what we're doing. So here's some example of them. Coarse wave division, they're actually showing an 18 channel, which is probably about as big as it is right now. So you can go on there and buy those right now. Oh. And then we have one last type. So remember your TV, and it hooked up and it had that connector that screwed into the back of your TV. That's coaxial. So coaxial, if you actually looked at it, is kind of weird. It's got a conductor here in the center, and then a bunch of insulation, and then this braid piece, and then this plastic on the outside. Coaxial actually has some advantages, weirdly, about how high a frequency we can put on it. So you may be getting your internet and your TV and everything all over this. So if you're using Spectrum or some of these, that's what you're still getting. This is the most common one, and this is what I'm making you guys work with in class. Probably shouldn't use the word torture, but Most of the time, we're going to have 4 pairs of cabling. So for our network needs, we're almost always going to have 4 pairs. If you have older phone lines, you may see that you have 2 pairs. And some of the older specs, we could actually use 2 pairs to get our signal across. We didn't need all 4 of them for the speed. And so what a lot of businesses did back in the middle 90s, late 90s, somewhere in there, was they said, oh man, we need more computers, and I know we're only using 2 pairs, so they would split those. And so they would have data on those 2, and maybe they have phone calls on those 2. And that worked okay. Until we came along and wanted to upgrade them to gigabit or faster networks that used all 8 wires, and all of a sudden the world comes to a crashing halt, and we have to add all kinds of new cabling in there. So that's where it has that idea, fast internet, or 100 megs per second, where it's divided up. But anything using gigabit or higher is all going to use all 4 pairs. It all lands under this TIA-EIA 568 group. So you may see TIA-EIA 568A or B, and those are our 2 most common types. So Cat3 we don't use anymore, gone. It was used really only for telephone. Even now, we still do some 5E because it's a little cheaper, and for some things, like network cameras, for example, it works just great. But if I'm going to build out a new office building, I'm going to say I'm going to start with typically 6 or 6A. 7 I would not go to yet. It's not really as well defined. Inside of my data closet maybe, but at that point I'm going to put fiber optics in for the most part. And then to make it even more complicated, we break it down into, they're both twisted pair, whether it's shielded or not twisted. So the stuff that you guys got to handle earlier in class, so that's one similar to this, is unshielded. Shielded adds, kind of looks like that coaxial, so we have our individual cables, 4 twisted pairs, and then it's got this foil shield and a braid. And then our connector on the end actually has a metal piece around it, so it's much more expensive. The only place, honestly, I recommend it is if we are in a high EMI area and fiber is impossible to put through the area. At this point, we can do fiber optic cables cheaper than we can do the twisted pair shielded. Let's just move to copper or to fiber in those places. So this is our examples of a couple different types. So what we're going to hopefully work on here is this core. I found my cabling, by the way, when I was down in one of the rooms. I was like, I had boxes of cabling. So if you notice the twists, so that's 5, this is 5E, but notice the twists are a little bit more on this one. And then finally when I get to that Cat 6, notice how tightly they're twisted. They're trying to get that more and more right angles instead of being beside each other. So here's a question. What's the difference between this and this one that says it's plenum grade? You guys ever heard the word plenum? When your guy comes and works on your air conditioner, you may say, hey, your plenum space needs to be bigger. So plenum is an air space. So when I look up here and I see all of those air exits, oh, that's great. We're getting air in. But where does the air come out of this room? And in most places, they use suspended ceilings or some areas as a way to get air back into the air conditioning system. The problem with traditional cabling like this one, like the stuff we're going to use, is if we get it hot enough or start to burn it, this PVC degrades. And one of the things it degrades into is cyanide gas. And apparently cyanide gas is bad for you. So typically most jobs spec plenum grade. So this is $200 a box, this is $300 a box. So it is more expensive, but not killing off your employees is probably a good thing. Couple of other quick pieces out of here is this idea of length. So typically, without any other means in here, we can only go 100 meters or about 330 feet of our cabling that we just built. So because of the time delay and the signal loss, that's about as far as we can go. And in fact, for 10 gig per second, typically we can't get that far on a cable. So, bless you. One of the things we're going to do, and you guys have already started on that, is there's terminations. So there are two basic standards. Why there are two? Because why not? To make life miserable. There's A and there's B. B is weirdly the most common. So here this chart shows A and it shows B. And if I'm thinking about this, there's my orange, my white, green, my blue, blue, white, green. So you guys have seen this in class. Those of you online haven't seen that yet. This looks very similar, and notice really what the change is. What's the one change in here really? The brown pair change? No. But notice the green pair does. Yeah. And the orange pair. So it's just a little different. As long as we wire both ends with the same standard, we're good. So that also tells you which ones were used in fast Ethernet and which ones we could break out. So we have even more of these pinouts. So straight through cable, a patch cable, just means that we've got A on one end and A on the other. That means it crosses straight through. A crossover is a cable that's flipped. So it's A on one side, B on the other. And we can actually connect a computer to another computer with a cable like that and not need to have a hub or a router or anything else. So that's a crossover. This one we don't see very much, but it makes a pretty picture. So notice they're completely inverted from each other. So for some devices, if I wanted to connect to it, they did this for like some kind of weird, obscure security purpose as far as I can see. But I, quite frankly, have not used a rollover cable in a long, long, long time. So be aware it exists, but you're not gonna have to make one. What is new and exciting for cabling is PoE. So power over Ethernet. So I can power my devices. So the camera that's up in the corner of the lab up there, that's actually not plugged in right now, just in case you're wondering. But the way it gets power is through the same cable. So I only have to run up that data cable, and it actually gets power through that cabling to run. So the access points in the hallway that you'll find, that's how they get power. So we can even run all kinds of pieces that way, running PoE. So PoE, typically you need Cat5 or better, but I don't have a ton of issues with places that do that. So a couple of ways we can do this. So here's an example of we're putting a PoE switch in. That provides data and power to that security camera. That's similar to what we have up here. The other model, so maybe I only need one camera and it doesn't make sense. What they're talking about is a device like this called an injector. And so you're seeing both ends of it. It's got an in and an out. And it's also got a power port. And so what it does, it's called an injector. And that means we have put power and data and we combine them separately. So it's not as clean, it's not as good, but if I only need a couple of them, it's not maybe worth spending the money to buy a whole new power over Ethernet switch. So that's the way we run some of those. And so then in this case, since it says it's a non-PoE camera, then possibly we actually have a device here to split out the power and the data separately. So that's what an injector looks like. That category is rated for how fast it is. So at this point in an office, I wouldn't even think about using 100 base T. So that stands for 100 megabits baseband T stands for twisted. So this, 1,000 bits per second, it also is twisted gigabit Ethernet. That's what our computers right now are on in here is gigabit, or 1,000 bits per second. So maximum distance, still the same. We get to 10 gigabit Ethernet. Well, now we're sending out a lot more data, uses all 4 pairs. It's 10 times as fast. And so there is actually one in between that's come out. And so your computers in front of you in the lab actually have this. So rather than go all the way to 10 gigabit, there's a 2.5 gigabit standard that's come out. And so I'm trying to find a switch or get one that we can purchase so we can see the difference between gigabit and 2.5 gigabit here in the computer lab. I've deployed that in some offices, and it's really nice in terms of pulling data and moving stuff around. And now we get to our buddy fiber. So let me look at one here. And that's actually a fiber right there. So each one of these little glass hairs you see sticking out are a piece of glass. So outside of that is what we call the cladding. So we call it the glass core. The cladding wraps around that, so that's this little colored piece here. And then we surround it all typically by either Kelvar or steel or something to shield it. And then we have an outside plant piece here to protect all of those pieces in there. And there's different kinds of cables, so don't think that they're all going to be like that. And they range anywhere from a couple fibers to you can get some with hundreds and hundreds of fibers in them, depending on what you want to do. So the light comes out of a laser, sends through the fiber. The cladding is really what's important there. That glass fiber, if I don't have anything to reflect that light back in, it's just going to shine that light all out and it's not going to go very far. What it really does is it reflects that light back, it protects that glass or plastic. We can use plastic in some short runs. So it sounds kind of hard to deal with. It's glass. Well, yeah, I can break it if I bend it too tight. So it's got something called a minimum bend radius. But it's got a lot of advantages. I can send more data over fiber than any other medium. It's got security in that it's harder for some agency like the NSA or the Russians to hack that or break into that. Okay, so it's harder to get into. Noise resistance, I can put it right by the light bulbs of the motors. And probably one of the biggest pieces is I can send it a long distance without having to re-amplify. At one point when we were using coaxial cables across the country for phone calls, there was actually, they called them power stations, and it was every mile. Can you imagine how many of those are that AT&T had to build if it's every mile from Los Angeles to New York City? All right. But there's some drawbacks. And really, this one I'm going to say is almost a push at this point in terms of price. They're very similar in price. What is expensive is the equipment to splice that. So if I'm fusion splicing it, I'm typically in at $10,000 to $20,000 for the splicers. Now, they make some mechanical splicings and some other things, so they've brought the price down. When I started in this field, it was easily $100,000 worth of splicing equipment before you could even think about it. So, fiber optic is the biggest output. Sometimes we think it's the most expensive, but on a long haul, it's actually at this point the cheapest piece. We can also go, and this number's out of date, we can certainly go past 40,000 meters at this point. However, what's interesting is the big reels of fiber, typically the longest reels you could buy were 40,000 meters long. So, again, typically 70 miles or so you could get to before you could splice them together with fusion splicing and then have to add a regen station. So there's two basic types of fiber. So there is something we're going to call single mode fiber, and single mode fiber is the smallest fiber we have. So a human hair is about 60 microns. This is actually like a tenth the size of a human hair. The advantage is, because it's so small, is that light, as it goes through there, doesn't have the opportunity to bounce around. And so that's its advantage. So that light goes in a single mode. Probably not the best drawing, and we can talk about why that is, but that's what we carry for the long distance communications. So if I need to go 70 miles, I'm going to utilize single mode fiber. It's more expensive to splice. It's more expensive in most regards simply because of that smaller size. It's a little more delicate. But all of our internet backbone is going to be single mode fiber. So multi-mode is about the size of a human hair. So it's significantly bigger. And what happens in that is those light pulses that come in here travel all over. They bounce and so they get through, but they lose a lot of energy doing that bouncing. And so when they lose that energy, that means they go much shorter. They have higher attenuation. But if I'm going to connect workstations, I'm going to connect my building, I can do a couple of kilometers pretty easily even with this. And so they're, in some cases, really, really cheap to use. So, again, that's that idea of how those signals come out. Multi-mode means there's multiple modalities of light that can be in there. And so, one's going kind of straight, one's all over. And if you think back to your physics classes, light does some really weird things, so we'll not get into that. Never mind. All right. So, we then have to deal with how do we end this cable? And so there's lots of different types of ends. So this little plastic cap here is protecting, that's that cladding. And so the fiber is probably right there at the flush at the end of that one, in this case. Sometimes some different models it's actually out just slightly. So that is that end piece that we're reconnecting. At some point, they're not all fibers fused. If I were fusing it, I really heat this up and I push them together, and I get a connection that has very little signal loss. But when I have to mechanically connect it, like I'm plugging in my adapters, I have to worry about what kind of connector I have. So because no matter what kind I have, I'm going to have some that's going to come backwards at that joint, at that junction. Think about when you look at a glass of water and that straw and you put it in the side and how it has that bend, or it looks like it does. That's what's happening here. You have what's called a refraction occurring. So how we deal with that depends on what kind of fibers you're using and how you're connecting it. So LC, now so right now they're saying the MMF connector. No, we're really at this point we're using LC more than anything. So LC looks very similar to what you see on the left over there. So it's a duplex jack, so it's got a send and a receive cable. This is just an adapter that takes an electrical signal, converts it to a fiber. I will show you guys here in class what one looks like. I can't really show it as easily. So there's another type of converter. Typically now, my brain still calls them GBICs, but they're different names. So SFP Plus is 10 gig or more. So they've got all these different new adapters that can plug straight into switches. So SFP Plus is 10 gig, XFP is 10. So some of these are even faster. The other thing that we can do, and I've had to do it quite a few locations, there's not enough fiber in the ground. And one way we can do that is by using what's called a bidirectional transceiver. In other words, I'm going to send data at 1350 nanometers on one signal going out, and I'm going to receive it at like 1550. So I'm only using one connection or one fiber. So it's kind of nice that I can do that. So most places did not accidentally overbuild. They underbuilt their fiber. So being able to do those single directional pieces like that is kind of interesting. So these are some of our standards. So it's got a lot of different segment lengths in here. Maximum transmission speed. So these are both 1000 megabits or a gigabit connection. How far you can go. 550 for multi-mode, 5000 meters for single mode. So, and these numbers are not hard in place because there's other ones that are different. So certainly I can get fiber now that's over this 40,000 meter mark from that same style. So I can also go much faster, and I'm going to pop over to the page and show you just how fast here we can actually go. All right. We're going to look at some of the tones and other pieces, but I'm going to jump in that in a little bit, because what I want to do is I'm going to actually go to a store. So I buy a lot of stuff weirdly from these guys. I really like them. And their prices are really, really affordable. But if I want, so I can buy what are called these transceivers. And transceivers come in a lot of different shapes and sizes, and so in this case, I can find all different kinds of things, and I'm going to look at these optical transceivers. And we'll show you guys physically one here from these guys, actually. Holy cow. So here's my 10, 25, and 40. 1, 2, 4 gigs. But notice now we actually have 800 gigabit per second connections available. So maybe I want to go to distance, and I want to go, let's see, where is that at? There's kilometers. I can pick this up, and these now are able to run 80 kilometers off of one of these GBICs. And I will tell you, that sounds expensive, but it's not. So that's sending 100 gigabits per second over 80 kilometers. So if I want to go faster than that, let me eliminate distance. But I want even faster data rate. I want to do an 800 gig one. You'll notice my distance isn't as far. So that one's 1310 nanometers. That one's 2 kilometers it can go. And for a mere 6,000. Now you're going, oh, that's a lot of money, right? Let's go to look at something that's a little closer to what we typically deploy around here. I'm not in the carrier information systems anymore, but what I do is a lot of 10 and 25 gig stuff. So let me go back to transceivers. And if I go to, come on. So if I look at something a little more reasonable, the prices actually are frighteningly low. Why are you doing this to me, page? There we go. I still want to do that. Come on. Page and I do not agree. So if I just get a 10 gig connector and I'm doing a short distance run and this fits my needs, that's 20 bucks. That's pretty darn cheap, honestly. And even the 25 gigs, not that expensive. So I can plug those into a switch and I can get that kind of connection really, really easily. So, and these guys do sell switches and all the different kinds of stuff, and I've bought from them. So I'm not a shill for them. They certainly don't give me anything, but it is interesting to see what some of these products look like. So it's kind of a fun little place to wander around in. So, all right, I'm going to hit end on my recording. There are two simulations